Okay, so I mentioned that I would like to just give you a brief reminder on how interval notation works. So let's recall the following. So start with two numbers. So for any real numbers, and I'll call them A and B, and the way I can write that is just to say for any A and B in the reals. And I want to actually be a little bit more specific. I want to specify which one's the smaller of the two numbers. So which one would be further to the left on the number line. So let's just say with A, the smaller of the two, so A less than B, right? So let's assume that that's already fixed in the background. Then I can write down the following. I can write down the open interval from A to B, right? And what this stands for is it's the set, and I'll write this in set-builder notation. This is an example of a situation where to write down the definition of this interval, you really need to use set-builder notation. So it's the set of all real numbers x such that A is less than x and x is less than b. In other words, it's the set of all real numbers x such that this criterion is true. So in other words, this is the set of all real numbers x such that x lies strictly between a and b. That's the definition of this note, what this notation means. So this is called an open interval. Okay, so let's underline that because that's a definition. And the picture, just for emphasis, the picture is going to look like this. Right, you've got the number line. Shall we just label it R for good measure? So A, let's say, is here, and B is here, let's say. So I want the points in between. That's what that interval is going to represent. And to be more specific, I don't want to include A, so I'm going to draw a big empty dot to indicate that. And I don't want to include B either. So that's usually how I would sketch an open interval. Okay, but you can also do closed intervals. And the only difference in notation is you just use square brackets instead of round brackets. So the closed interval A to B is just the set of all real numbers x such that, and I'll really write the same thing down except the inequalities are going to be non-strict this time. So it's the set of all real numbers x such that A is less than or equal to x and x is less than or equal to b. So in other words, it's the set of all real numbers x such that x lies between A and b with where we allow for the possibility that that x is either equal to A or equal to B. So this is called a closed interval. Okay, and let's just sketch a picture of that as well. So this is your reminder on interval notation. So it's going to look almost the same, except we want to include A and B this time. But other than that, the picture won't change much. So I'm going to get shade the points between A and B. But since I want to include A, I'm going to do a solid dot here. And since I want to include B, I'm going to do a solid dot there. So that's interval notation. Okay, let's move on to this example here. This is an example of a function that's defined using a little bit different notation. So let's read this carefully. Define y as a function of x using the rule y is equal to the square root of x. So notice you don't see like the f of x notation that we had in the previous example, right? We're actually just using a single letter to represent the output value. So y represents the output value and x represents the input value. So when you see y as a function of x, that's really what that means. Here's your output and here is your input. And we could still use equations to define the rules. So this is still the function that takes as input some number x and then it outputs y, which is given by the square root of that input value. So the way the function works is you plug in a number, it takes its square root and gives you back the result as output. Okay, so let's start by answering the question, what is the domain of this function? Well, this is an example, and I alluded to this on the last page. If you're not told explicitly what the domain is, like in this case, right, we aren't told the domain, so how do you find the domain? Well, it's going to be the biggest set you could possibly take in which all those points make sense. So let me phrase that a bit more carefully. It's just the set of all input values for which this rule would make sense. That's what our domain is going to be. And you'll notice that this is going to make sense. So in other words, the square root of x is defined under what circumstances? It's defined exactly when that number x is greater than or equal to 0, right? Because you can't take the square root of a negative number. That's an important property about square roots. So that's how we can get to this point. So if the square root of x is defined exactly when x is greater than or equal to 0, well, that means this rule is going to make sense exactly when x is greater than or equal to 0. So we can say the domain is given, and if we want to write our answer as a set, we can use the letter D to label it, although it's not strictly necessary. We could write it in interval notation. We could say this is the, well, I notice I'm using a square bracket on 0. And I don't actually put a right endpoint. I use the infinity symbol for the right endpoint, just like we did on the previous page. That just indicates that there is no upper bound. I can take 0 and every positive number to be in the domain. So if I wanted to state this in set builder notation, I could write it this way. Although you don't, let me emphasize, you don't have to do both of these. If you choose to write your answer in interval notation, you don't now have to write it in every other possible way. You can just pick whatever format you like, but I'm going to give you both here so that you can pick whichever one you'd prefer to use. So if I want to write this in set builder notation, I'll say D is the set of all real numbers x such that x is greater than or equal to 0, because that's really the only requirement that we're going to put on elements of the domain of this function, right? So that's how I can write it in set builder notation. And of course, I'll just to be complete here, I want to also draw the picture. So I got, and this is a reminder about what this notation would mean. If I put an infinity symbol as one of the endpoints, that just means there's no upper bound here. So I have, say, the number 0, and it's a square bracket on 0, so I want to include that point, and then I'm just going to shade forever in this direction. So that's how I can express it as a picture. So again, you've got interval notation, you've got set builder notation, and you've got graphical notation. You can write your answer in any of those 3 formats, and you don't have to do all 3, right? Just pick your favorite one and use that, and that's completely sufficient. If you want to do all 3, go ahead, but you're not required to. Okay, so that's the domain. What about part B? We're asked to evaluate these things. What does this notation mean? Well, that's actually, to answer that question is really the purpose of this example, just to remind you what this notation means. If you haven't seen it, I'll tell you right now. So if you see y, something like that, and then a vertical line, and then x equals 0 down here, what this really means is the value of y when x is equal to 0. This means the value of y when x is equal to 1, and so on, right? That just means, in other words, just evaluate this function, but plug in x equals 0, x equals 1, x equals 2, and x equals 4. Plug all those values into the function and determine their corresponding output values. So that's all it is. So let's practice using this notation. If I want to go y when x is equal to 0, so that's the value of y when x is equal to 0. How do I determine that? Well, just plug x equals 0 into this rule, and you'll be able to determine what y has to be. So this is going to be the square root of 0. And what's the square root of 0? It's just 0. Okay, so that's all there is to it there. If I want the next one, the value of y when x is equal to 1, well, plug x equals 1 into this rule. So you're going to get the square root of 1, which is 1. Okay, that's all there is to it. So now what about y when x is equal to 2? That's going to give you the square root of 2. And, well, there's no nice number. There's no nice whole smooth number that you can square and get 2 back as the answer. In fact, it's a weird irrational number. It's roughly 1.4 something. I forget the decimal places exactly at this point, but who cares, right? Just leave it like this, the square root of 2. You're not going to be able to write it any better or more exact than that, right? So that is the answer, square root of 2. That is the value of y when x is equal to 2. So just stop there. Don't resist the temptation to plug it into your calculator. If you'd like, or let me say that differently. If you want to plug it into your calculator and figure out a decimal approximation of this number just so that you can wrap your head around it a little bit easier and get an idea for its size, that's absolutely fine. In fact, I would encourage that. However, it's not going to play a role in the way you write your answer, right? This is where you want to stop. You want to stop with the square root of 2 because that's exact. Okay, but we got one more, the value of y when x is equal to 4. So this one, on the other hand, this one works out quite nicely. Because the square root of 4, which is what I get if I want to work out the value of y when x is equal to 4, I'm going to plug x equals 4 into this rule. I get the square root of 4, that's going to be equal to 2. Because the positive number who when you square it you get 4, that's going to be 2. right? Notice I don't say plus or minus 2 here, because if I have the square root of 4, this automatically means the positive number, who when you square it gives you back 4. And that, of course, is 2. Okay, so that's the end of that example. So that's really, again, the point of this was just to remind you what this notation means. It's very much like this notation on the previous page that we evaluated functions at points over here, except it's just in the case where you use a single variable as the output value, then you might use this notation to write down point evaluation of the function. Okay, so we've got one more example on this page. This one, find the domain of each function. There's actually part B on the next page, but for now we've just got this function given by f of t is equal to 1 over t squared minus 1. That's your fraction. So this is going to be another question of what values can we plug into this function and have it make sense. That's our job. We have to figure that out, and that's going to be how we find the domain. So let's do that. Well, start by making this observation. F of t is defined when? Well, when, let me put this, whenever, and then we can finish the sentence down here. Well, let's look at it. It's a fraction, right? You've got 1 over t squared minus 1. When is a fraction defined? It's defined as long as the denominator is not 0, right? So we need to just make sure that this t squared minus 1 is not equal to 0. So that's going to tell us when f of t is defined. So f of t is defined whenever t squared minus 1 is not equal to 0. So let's figure out when is this going to be true. For what values of t is t squared minus 1 not equal to 0? Well, if you want to answer that question, start by solving the reverse of this statement. So solve the equation. Let's look at t squared minus 1 is equal to 0. Okay, so solve that equation. And that's really going to be how we answer the question. So whenever the solutions to this equation are going to be precisely the values for which this statement is false, and those are going to be the values that aren't in the domain. So let's solve this equation. We'll start by adding 1 to both sides, so you can get t squared is equal to 1. And then you're going to ask the question, okay, well, to solve t squared equals 1, what values of t satisfy that equation? Well, you're going to get t is equal to plus or minus 1, right? So notice here I did include the plus or minus, right? If I've got an equation t squared equals 1, and you can think of it as taking the square root of both sides to get to this step, or you can just answer it by inspection. But either way, in this case, you do add the plus or minus. But up here, if you're already seeing a square root, if you're given a situation where there is a square root already, then you don't do plus or minus. You just automatically take the positive of the two values. So that's why up here we didn't say plus or minus 2. We just said 2. But over here, because there's no square root, we're actually solving the equation t squared equals 1. We want to make sure we get both values. Okay, and don't be afraid to come to reach out and send me a message if you're not sure why that is that way, or you'd like me to elaborate a bit more. Have a conversation with me. We can go into more depth on that. Okay, but those are the values that make this equation true. So that means these are the values that make this statement false. So that tells you what the domain is. Okay, so we can now write the domain down in any way. Well, we have 3 methods, right? We can say the domain of f is the set of all real numbers t such that t is not equal to plus or minus 1, right? That's really what you're talking about. Now, what would the picture look like? I actually really want to, this is probably the last example where I'm going to go to the point of drawing or writing down every single method of expressing the set, but I want to make a point here. So I'm going to draw the picture down here, and then we can write the domain in interval notation right in the middle. Okay, so we want everything except those 2 points. So let's put open dots on -1 and 1, and we'll just shade everything else. So we want all these points. We want all the stuff in the middle. And then we want all the stuff over here as well. So visually, that's the domain of this function f. It's everything on the real line except the -1 and +1. So how would I express that in interval notation? Well, you'd have 3 intervals here, right? This is one interval. So let's say, or we can write the domain of f. Let's write this as an interval, just this one piece down here. So the left endpoint's going to actually be -infinity since it goes forever in the negative direction. So I'll say -infinity all the way up to -1 with a round bracket because I don't want to include -1. Okay, so that interval represents this piece here. But I also want to get this piece in the middle between -1 and +1. So how do I paste these intervals together? I do it with a union symbol, right? So I want to take the union with the open interval from -1 to +1. So that interval gives me this piece, that interval gives me this piece. Then I'm going to do one more union because I want to express this piece as an interval now. So this will be unioned with the open interval from 1. And then, again, it goes on forever here. So the right endpoint's just going to be infinity. Okay, so that's how you can express the answer. And again, all three of these are fine. You've got set builder notation, interval notation, and graphical notation. All three of those methods are completely fine for expressing the domain. So that's the last example where I'll write all three versions. I'll just pick my favorite and usually I'll do my answer in interval notation usually, but you're free to use any of those three formats.